Hello everyone, welcome to lecture 15 on numerical analysis. So far we are dealing with the solution of system of linear equations, that is solution of simultaneous linear algebraic equations. So far we have seen what is linear equation, system of linear equation, and when it is solvable by iterative method, and we have seen Jacobi-iteration method and as well as Gauss-Seidel methods, and we have given a comparison between the Gauss-Seidel and Jacobi-iteration, as well as we have seen one example, okay, solved by Jacobi-iteration method, and the same example we have solved by Gauss-Seidel method also, and we got the approximate values of the roots. So we have seen what is Gauss-Seidel method and how to operate the Gauss-Seidel method. Okay, so here in the after obtaining x1 we are replacing by x0 by x1 in the y1. Okay, so this is how we have solved, and we have solved this example too. Also, we have seen what is the difference between Jacobi-iteration as well as Gauss-Seidel method. So now we shall continue with the next example. That is example 3, solve the system by Jacobi as well as Gauss-Seidel method. So both the methods have been asked. Okay. So first we shall solve this system by Jacobi-iteration method. So for that, okay, what is the system given? 8x minus 3y plus 2z equal to 20, 4x plus 7y minus z equal to 33, 6x plus 3y plus 12z equal to 35. So let us solve this by Jacobi method first. Okay, right. So since the diagonal elements are diagonally dominant, see, diagonal elements are dominant, so we can write them for the expression of x, y, z. Okay, since the diagonal elements okay, it is diagonally dominant, therefore the diagonal elements are dominant in the coefficient matrix. Since the diagonal elements are dominant in the coefficient matrix, so we write x, y, z as follows, x, y and z as follows. Okay, so we have x is equal to, so from this equation let us solve for the first equation, let us solve for x. So x is equal to 1 by 8 into 20 minus 20 plus 3y minus 2z. Okay, so treat it as equation 1. So next solve for y using second equation. So 1 by 11 into 33 minus 4x plus z. Okay, so treat this as second equation. So next solve for z using equation 3. So 1 by 12 into 35 minus 6x minus 3y. So this is equation 3. Okay, so once these three are obtained, so next we can process by the iteration method. Okay, so taking initial values, since we are dealing with the Jacobi method, so by Gauss-Jacobi or Jacobi method, Jacobi iteration method, So, note carefully, first we are dealing with Jacobi-iteration. Jacobi-iteration means use the initial values throughout the iteration. Okay. Yeah. For first iteration, so first we need to consider the initial values. So let x equal to 0, y is equal to 0 and z equal to 0 be the initial values, be the initial values. Okay. Yeah. So now after taking x, y, z as a 0 as initial values, so we go for the first iteration. We go for the first iteration, right? So first iteration. So for first iteration, so we have x0, y0 and z0 as eigenvalues. So using initial values in 1, 2, 3, using initial values in 1, 2 and 3, so we get. So what are 1, 2 and 3? So these are the values 1, 2, 3. Okay. So put y0, y as 0 and z0. So then we get x1. In place of in second equation, put x0 and z0. We get y and so on. Okay. Using initial values in 1, 2, 3, we get. So the first iteration, that is x1, is equal to. So what is the expression? 1 by 8 into 20 plus 3x. Okay. So 3 into 0 minus 2 into 0. So this gives us what? 2.5. Calculate using a scientific calculator. So now let us go for y1. So y1 is 1 by 11 into 33 minus 4 into 0 plus 0. See, while calculating y1 I am still using x0 and y0s. Okay. So because we are dealing with Jacobi method. Okay. So we get this as 3. So next one is Z1. Okay. So Z1, so I read Z1 like Z like this because to distinguish between 2 and Z. Okay. So I use this Z cross like this for Z. Okay. So to distinguish between 2 and Z, right? Yeah. So don't confuse with this one. This is Z. So this is 1 by 12 into 35 minus 16 into 0 minus 3 into 0. So this gives us 2.9166. Yeah. So we have done with the first iteration. First iteration is nothing but using initial values 1, 2, 3. In 1, 2 and 3 we get this first iteration. So now let us go for the second iteration. So for second iteration use x1, y1, z1. So second iteration, so use x1, y1 and z1 in 1, 2 and 3. So we get x2, x2 is 1 by 8 into 20 plus 3 into 0.3 minus 2 into 2.9166. So this gives what? 2.8958. So next we shall go for y2. So this is 1 by 11, 33 minus 4 into what is x1, 2.5 plus this z value 2.9166. So this gives what? 2.356060. Okay. So now last one we calculate z2. So z2 is 1 by 12, 35 minus 6 into x, x1 is 2.5 plus minus it is minus 3 into 3.0. So this gives 0.9166. Okay. See, we can see where this has been jumped. Z1 is 2.9166 to 0.9166. Okay, see where the jump has been occurred. This is 3 to 2.35551 and x1 2.1 to 2.8958. So this is second iteration. So now let us continue for the third iteration and so on. Okay. So once this iteration is set up, then everything is done by the calculator. We just go on writing the iterations. Okay, the third iterations. So for the third iteration, so we use x2, y2 and z2 in equations 1, 2 and 3 respectively. We get x3. So x3 is equal to, again write this formula 1 by 8 into so on. So I just give you the value. The x3 is okay. Let us once again do with x3. So later for the iteration onwards, I will just write the numbers. So 3 into what is y2 2.356060. Okay. So minus 2 into what is z, 0.9166. So this gives 3.154356. Okay. So next y4, not next we have to go for what? y3. Got to go for y3. So we get, okay. So next y3. So y3 is 1 by 11. So 33 minus 4 into 2.8958 plus 0.9166. So this gives 2.0303. Okay. So next we go for finding Z3. So Z3 is what? 1 by 12 into 35 minus 6 into what is the x2 value? 2.8958 minus 3 into what is x value? 2.3560, y value 6060. So this gives 0.879735. Okay. See, now we have obtained the 3 iterations, but the root has not yet converged. So here 2.5 in x1, 2.89 and 3.15 root has not yet been conversed. So we can, what we can do is, for sake of saving the space, so we can make a table as we did in the bisection method or the Newton-Raphson method. So we can make a table of iterations, like this. Okay. So table of iterations. So the first column iterations. So this is x value, y value and z value. So in the first iteration, what is the x value? 2.5, 3 and 2.9166. Okay. The first iteration 2.5, 3, 2.9166. The second iteration, what do we have? X, y, z values 2.8958 for iteration 2. So we have x value 2.8958, y value 2.356060 and z value 0.9166. Okay. For the third iteration, what do we have for the third iteration? So what is the value we got for the third iteration? So x value is, what is x value? 3. For the third iteration, x value is 3.154356. Okay, and y value is 2.0303 and z value is 0.879735. So this way of writing in table gives, means we while writing in table we can see where the root has been conversed. So root has not been conversed yet, so we go for the fourth iteration. So that I write it in the directly in the table. The fourth iteration gives x value as 3.04143 and y value as 1. The fourth iteration, x value is 0.0. Okay, 3 iterations are over. The fourth iteration, see, it is 1.98. The third iteration is over. In the fourth iteration, it is 3.04143 and y value is 1.9329. Okay, and z value is 0.83197. Right? Yeah. So we can see that the root has been not conversed yet. So let us go for the next values. So next iteration, fifth iteration, the x value is 3.016873 and y value is 1.9696 and z value is 0.912717. Okay. So still the root has not been conversed yet. So let us go for the next iteration. So sixth iteration, the sixth iteration x value is 3.010441 and y value is 1.9859. So z value is 0.915817. Okay. So now we can see here in the fifth iteration x value is 3.01, 3.01 and y value is 1.96, and this can be made as a 1.97 also, 1.97, and it is 1.98. So this is 0.91 and 0.91. So if you want we can stop the iteration here itself. So but still we go for the seventh iteration to get the more accurate values. The seventh iteration x value is 3.015770, y value is 1.988550, and z value is 0.914967. Yeah, so now we can see in the 567, so the root has been converged up to 2 decimal places. So we can take it as 1.98, 0.91 and 3.01. So therefore, so iteration table always help us to see the convergence. Okay. So therefore, the approximate values are x is equal to 3.01, y is equal to 1.98 and z is equal to 0.91, correct to 2 decimal places. Okay. So if the required degree of accuracy is asked for the 3 decimal places, then we have to continue the iterations. Okay. So therefore the always iteration table, that is table of iteration, will help us to understand the convergence, and we can write this way in the exam also. But you have to calculate first few iterations like this in the full form for each x, y, z, and next iterations you can tabulate them, and we can see the convergence where the convergence has been occurred, and we can approximate the rows. Okay. So this is how we have solved this example by Jacobi-iteration method. Further, we shall see that how to solve the same example by Gauss-Seidel method. Okay. So now by Gauss-Seidel method, so we are seeing this example by Jacobi-iteration. Now by Gauss-Seidel method. Okay. So in the Gauss-Seidel method, what we do, we write this x, y, z. Okay. This we take it as 1, 2, 3 as it is, and we take y0 and x0 only. So we don't take x0 as the initial value because we are going to calculate x1 immediately. Okay. So for Gauss-Seidel method, we take y is equal to 0 and z is equal to 0 as initial values, Okay. So after this we immediately go for calculating the first iteration, because we don't need x0 here. Okay. Because we are going to calculate the x1, we don't need a first in the first iteration. So first iteration, so use these values, use these y0 and z0 values, these values in equation 1 only. Earlier we used to write equation 1, 2, 3. See, equation 1, 2, 3 here also, and equation 1, 2, 3 here also, and equation 1, 2, 3 here also. But now while using Gauss-Seidel method, we are using equation 1 only, because after using equation 1 we get x1. Okay. And equation 2 also, because z0 we are using, not equation 3. So we get first approximation or first iteration as, so x1 So x1 is what? 1 by 8. See, in the x1 we are going to use y0 and z0. In the x1 we are going to use y0 and z0, 0 minus 2 into 0. So, we get it as 2.5. So, this is same as we get in the Jacobi-iteration method. But in the y1, in place of x0 we are going to use x1. So, this is going to be 1 by 11, 33 minus 4 into 2.5 plus 0. So, this is going to be z0 still we are using. This is going to be 2.0909. Okay, now let's just compare this y1 in the Gauss-Seidel and y1 in the Jacobi-iteration. In the first iteration of Jacobi, see y1 we are using both x0 and z0, but in the Gauss-Seidel method for y1 we are using x1, okay, and z0. So, this is a difference between Gauss-Seidel and Jacobi-iteration. So, similarly, while calculating z1, see here we have used y0 and z0 in equation 1 and 2 only. So, now this is the third equation. So, z1 is 1 by 12 into 35 minus, we are going to use x1 instead of x0, that is 2.5 minus 3 into 2.0909. So, this gives 1.143939. Yeah. So, you got the difference here using x1, this is nothing but the x1 and this is nothing but the y1. So, whereas in the Jacobi method we have see there in the Jacobi method we are while calculating z1 we are still using the initial values x0 and y0. Okay. So, whereas in the Gauss-Seidel method while calculating z1 we are using x1 and y1. Okay. So, this is the first iteration. So, next let us go for the second iteration. Second iteration, use these values, use x1, y1, z1 in 1, 2, 3, in 1 and 2 actually. Okay. So, x2 is what? 1 by 8 into 20 plus 3 into 2.0909 minus 2 into 1.14393. Okay. So, this gives 2.9981. So, calculate y2, 1 by 11 to 33 minus 4 into 2.9981 minus 1 not minus plus it is. So, plus what is z1 1.143939. So, this gives 2.0137. Okay. So, next let us go for calculating z2. So, while calculating z2 use x2 and y2, 1 by 12 into 35 minus 6 into 2.9981 minus 3 into 2.0137. So, we are using the latest roots, latest values of x, y we are using in z. Okay. So, this gives 0.9141, okay, 7. So, what was the roots value? Correct, it is 3.01, 1.98, 0.91. Okay. So, this is approximately 3 and this is approximately 2 and this is approximately 0.91. So, the root if you want to correct it to two places. So, now see in the first iteration as well as in the second iteration. Okay. Now, let us go for the third iteration. So let me have the table for the third iteration. So table of iteration. So in the table of iteration, so I have iteration, and this is an x value, this is y value and z value. So already in the first iteration we have so far obtained the two iterations. The first iteration, what is the x value? Is 2.5, y value 2.0909 and z value 1.14393. Okay. The second iteration, so we have x value 2.9981, y value 2.01377 and z value 0.91417. Okay. So in the third iteration, I just mentioned the values. Here. In the third iteration, the x value what we get is 3.0266, okay, and y value that we get is 1.9825 and the z value that we get is 0.90772. Okay. So now let us go see what are the values for the fourth iteration. In the fourth iteration, we have x value as 3.016512 and y value as 1.985607 and z value as 0.912009. Okay. So in the fifth iteration, so I think almost the root converges in the fifth iteration. So now let us see in the fifth iteration, the x value is 3.016600, y value is 1.985964 and z value is 0.911876. Okay. So now let us observe the fourth and fifth iterations. So here 3.016, 3.016. In the fifth iteration, y value is 1.985 and 1.985. In the fifth iteration, and z value is 1.912 and this can be approximated to 0.912 also. Okay. So therefore we say that the root has been converged and the approximate values are, so x is equal to 3.016 and y is equal to 1.985 and z is equal to 0.912. And we may see that in the Jacobi method we have obtained approximate roots at the seventh iteration, that too corrected to 2 decimal places. In the Jacobi method we have obtained at the seventh iteration that too corrected to 2 decimal places. Whereas in the Gauss-Seidel method we have obtained the approximate roots in the fifth iteration itself, that too corrected to 3 decimal places. Corrected to 3 decimal places. So by seeing this, we can say that Gauss-Seidel method converges faster than the Jacobi-iteration method. Okay, by seeing that, what we can see, Gauss-Seidel method converges. Converges means it gives the roots. Converges faster than Jacobi-iteration method. So, this we have to keep always in mind that Gauss-Seidel method converges faster than Jacobi-iteration method. So, hope the example is clear by Gauss-Seidel method as well as by Jacobi-iteration method. Okay. So, we have solved this system by Jacobi-iteration as well as Gauss-Seidel method. So, both are different and can be asked in the example. So, they do not combine the Jacobi and Gauss-Seidel. So, they just ask either Gauss-Seidel or Jacobi. So, you can write any one. So, using this. Okay. So, table of iteration, first few iterations you have to do manually, then we can give the table of iterations like this. Okay, and approximate values. So, this is by Gauss-Seidel method we got the roots at the 5th iteration itself, that to correct to 3 decimal places. Therefore, we can say that the Gauss-Seidel method converges faster than Jacobi-iteration method. Okay. So, we shall see the next example in the next lecture. Thank you.